This is a very brief lecture. I have kept it so because I want to emphasize on a very important point. Okay, so, in the case of thermodynamic transformation, so I will try to contrast free expansion, also called the Joule expansion, against quasi-static expansion. Okay. So, in a previous lecture, we had addressed work transformation. We have all the work transformation can be represented as a product of generalized force times generalized displacement. These are intensive variables and these are extensive variables. Okay, so we've done this in the previous lecture, and we had emphasized three aspects of reversible transformation. One, that is infinitesimal, and then when a cyclic transformation is taking place, the system comes back to the same position in terms of thermodynamic state. Not only the system comes back, the surrounding should also come back to the same state. Okay, so that is another indicator of reversible transformation. And then during the transformation, all states should be represented in the state diagram. All right. So this is what we had discussed in the previous lecture. So let's come to free expansion or Joule expansion, right? So what is that we're looking at? There's a chamber here. This chamber is filled with gas at, let's say, pressure Pi, and this uh, volume is Vi, all right? So on this side of the chamber, there is nothing, there is no gas. Let's say, to begin with, there's vacuum, and both the chambers are separated by a partition. And then let's say you allow this partition to be removed. Okay, the partition is removed in some manner. At the final state, all right, so that this gas comes to this side gradually. In the final stage, the pressure is P final and the volume is V final, all right? So the initial state and the final state are well defined. But what you have to understand is the thermodynamic variables are not defined during free expansion. That is, when the gas is coming to this side of the chamber, the entire system has different pressures. Okay, so the intensive variables take different values inside the system. So that's what brings in the flow. All right. So this is not a reversible transformation. This has other many features of irreversibility, like viscosity and so on. All right. So certain losses. Okay, so these are not characterized thermodynamically using equilibrium thermodynamics. All right. So it is important to understand during free expansion, the thermodynamic variables, that is in terms of pressure and temperature. Okay. So they are not well defined. Okay. So there can be low pressure on this side, and there is high pressure on one side, which is what makes the gas flow from this and side of the chamber to this side of the chamber. Okay. So when we are thinking about PV work transformation, this is not the kind of transformation we are talking about. Okay. So what we are talking about is reversible transformation. So I'll emphasize the 2 points. One, it being infinitesimal. So what does it get us? Okay. So supposing in the initial state, the pressure inside is balanced by a weight. Okay, so exactly, so there is pressure times area, there is force, and the weight times, let's say, gravitational constant, mg. Okay, so is at these are well balanced, so nothing is moving. Okay, this piston is not moving. So we remove this part of this pile of mass, so that you can create an infinitesimal driving force for expansion. See, what is important is, oh, this mass looks bigger, right, than I mean, maybe it looks big, whatever is remote. So you may argue that it may not be an infinitesimal driving force. But in principle, you can make this mass that is being remote as fine as possible. Okay, so this can be fine pebbles or grains of sand and so on. So that what is important to understand is this system is expanding. Okay, so this piston is moving up, but the driving force for expansion, okay, is very, very small. Okay, so there is a negligible driving force for expansion. That is, if you add a pebble, okay, so it will get compressed. If you remove a pebble, the system will expand. Okay, so there is only a differential driving force in expansion, for expansion in this case, because of which there is quasi-static change. Okay, so this change is infinitesimal, and this will in principle it will take or in practice it will take infinite time to make this change. Okay, because the driving force is infinitesimally small, right? So this is just a thought experiment, but it's a very useful conceptual tool. Why? Because during the act of transformation, all the states, okay, so again, it has infinite number of states you can think. Okay, if you have a line between 2 points, there are infinite number of points. All states are well defined in terms of thermodynamics. Okay, so all the states can be plotted in the state diagram during the transformation. Okay, so when we are talking about quasi-static PV work transformation, we are talking about these kinds of transformation which transform due to an infinitesimal driving force. Okay, so we are not really talking about these kinds of transformation. So here the endpoints and the initial and endpoints are well defined. Okay, but the in-between points are not well defined. But in this case, not only the initial and endpoints are well defined, even the in-between states are well defined. Okay, so this is something which you should understand very clearly. I mean, there's a point when I was an undergraduate student, when I looked at thermodynamics for the first time, these are the issues which used to bother me. I mean, at least in the textbook I used. So I am just emphasizing this point so that there's no confusion in this issue. Okay, so thank you.